Adrian Rowland, who's in Singapore. Parts of it are very mathematical. I will not go into that. I will keep the talk as much intuitive as possible for the entire duration. So two things to start off with. Dynamics is a word that we all understand in terms of real life. Networks keep changing all the time, and I want to understand in our heads how a network changes and how to identify changes in the network. The word graphon is from dense graph theory. It's limits of dense graphs. I will explain this concept as I go along this talk. So there are two things here. Dynamics happens over time, and the number of vertices get larger and larger. So I have an n dynamics as n goes to infinity, and I have a t dynamics as t goes to infinity. Okay. So the first thing we should all keep in mind is what our favorite network is. So on this side, I've drawn a bunch of networks. So they correspond to a food network or a political network or LinkedIn or any professional network. So though I have drawn this and I have not matched name to network, that's not quite important, but each network has a certain structural property. So one must understand the structural property of the network to understand dynamics. So more than what each network corresponds to, I would just request that you, in your mind, you have an idea of your favorite network, whichever it is, either internet or your LinkedIn profile, how it looks like, or your Facebook network, or your friends in your society, your workplace. Just think of how the network looks like and how many edges it has per person, anything like that. This is from a nice sampling network course that I picked it up from. Here itself you can see, for example, this graph right here has, in the middle it has lots of edges, right? And people outside here are connected by a single edge into the network. So there's sort of a structural difference already there. Here the graph looks like, locally looks self-similar, and they're all connected to different groups in a certain way. So they're all structural property network that I like to identify. And just think of it as the network is moving, there's on and off happening, and I want to understand how the network moves. Okay. So again, I'm looking at large-scale macro properties of the graph. I'm not looking at locally into the graph and seeing what's happening nearby. So for me, just one second. Could you just not speak? I can't, I'm distracted. All of you, please, don't mind. So for me, a graph is of three types. Okay. So one is, I'll think of it as extremely sparse network. That means there are n vertices, and the number of edges is of order n itself. So there are very few edges in the graph. So I will give an example of a graph which has this property. So you can think of your favorite graph as something, a graph that has bounded degree. Let's say all your friends have only at most 3 friends, or 2 friends or 1 friend. Then your graph will have at most 3n edges. That's what I mean. Then the next thing I want to understand is what's called a sparse graph. So here, a sparse graph again has n vertices, but the number of edges will be a little bit more. It will not be order n. I'll have order n to the 1 plus alpha, where alpha is between 0 and 1. So some people will have large degrees in this network. Otherwise, the graph will be, rest of the graph will look like the extremely sparse world with bounded degrees, but few people will have large degrees. That's what I'll call as a sparse world. Then the last one I liked is the dense network. So here, what I'll do is, I want to compare it with the maximal graph. So what's the maximal graph? You take n vertices, and everybody is connected to everybody, right? So each person has n minus 1 neighbors, right? That means there are order n squared edges, right? So a dense graph will be like the complete graph, so it will have n squared edges. Okay. So these are the 3 regimes that I like to think about. If I give me a graph, I'll try to place them in these 3 regimes, and throughout this talk, I will illustrate properties of each regime to understand the macroscopic property of the graph in some sense. Okay. So I'll tell you key signatures to understand in each graph, each regime. And the signatures is what I will understand with regard to the dynamics. And I'll show you that if the dynamics, if the graph changes in some way, the signatures also will change in a certain way. Okay. So I will mostly focus on the dense regime in this talk, but I will discuss the following two regimes as well. So, and please feel free to interrupt me if you have any questions. I'll be happy to answer. Okay, here's the first example of a graph. I drew a graph. It's just a tree. It's a simple tree. I drew a sort of a non-regular tree. So, for example, here, if you look at it, this vertex has 3 neighbors, so degree is 3. I come down here, this vertex has 2 neighbors, one above and one below. These people right here have only 1 neighbor each, so degree is 1. So the entire graph has bounded degree. The highest degree is 3. So if you have n vertices, you can't have more than 3 n edges in the graph. So that means this is a sparse graph, extremely sparse graph. So it has order c times n edges, where c is some constant positive. Right. So for example, it need not be a tree. You could also have what's called a deregular graph. Like you could take a triangle, it's a 2 regular graph. These are also sparse graphs in some sense, extremely sparse graphs in some sense. Then if you're a physicist, you'll immediately recognize this graph. This is the famous Albert-Barabasi model, which I've simulated. Of course, it's a bad projection on the picture. Barabasi spelling, I hope it's correct. Okay. So they proposed a famous model in the early 2000s. So these graphs, you can construct them in an organic, inductive way. As a new vertex comes, you give it half edges, and you give half edges to a random number of vertices in the existing graph, and you pair them up. And you do them in a clever way, you will get order n to the 1 plus alpha edges. Okay. And so there's a power law of decay in the degrees, and they establish this in a seminal paper. And though it looks tree-like, the people here are very densely connected. They have lots of high degree vertices in this structures. Okay. So graph sort of spreads out. So here the key is that this is achieved in the following manner, that there are few degrees with few vertices with high degree. That's how this feature is achieved in this graph. Okay. Then I'll come to the dense regime. So this, since I'm a probabilist, I'd like to think of a neat, simple example of a random graph that we can work with. So this is a famous example of Edosh and Rennie. And this came out in the 1940s. And it's one of the most well understood random graphs. And it's so fundamental that anybody can work on it immediately. Like today you can go home and start simulating this graph and understanding what happens to it. So what's happening in this graph is that you have n vertices, 1 through n. Okay, and then you pair up vertices as edges with probability p. So what you do is you go to a vertex I, you go to any other vertex j, right? And then you say I have an edge between them by tossing a coin. You toss your favorite coin with probability p heads, and you place an edge with probability p. And one crucial feature is that it's happening in an independent way. So that means you're a friend of x, and x is a friend of y, has no effect on you being a friend of y. They're all independent edges. That's one of the more attractive features of the model. It's very simple, and that simplicity gave rise to a very rich theory in this. I'll try and explain the theory in a second as I go along. So the idea is clear. I have n vertices, and I go to any pair of them. I place an edge with probability p. That's all I'm doing here. So the simple model, if you simulate a graph with 100 vertices, and I put probability half for every edges, you'll see lots of edges in this graph. So why is that? Let's think a little bit. You have a vertex, one vertex, right? It has n minus 1 possible neighbors, right? So the degree of the vertex is just binomial with parameter n minus 1 and probability p. So expected number of edges from a single vertex is n minus 1 times p. There are total n vertices, so it's n times n minus 1 p is the average number of edges you expect. So let's just write this down. So the expected number of edges is a simple binomial calculation. Number of edges is of the order n choose 2 is exactly equal to n choose 2 times p is of the order n squared times p. So it's a dense graph. There are lots of edges typically. If you have a fixed p and you have some n, you'll have order n squared p times edges typically. That also can be shown. It's well studied that the graph concentrates around the mean, and there are very interesting analysis about this. But now there's a way to play with this now. So here I took p equal to half. So that gave you n squared times p. But suppose I vary p with my n, then this may not be order n squared. Right? So let's say I make p smaller and smaller as a function of n. Let's try and see that. So this is what I just said now, that if the number of edges, expected number of edges is of order n choose 2 times p, and this, let's say modulo, if Pn is like C by n, if I make my probabilities go down to 0, like C by n, so the larger number of vertices I have, I connect them with smaller and smaller probabilities, n choose 2p becomes n times p. So now I'm in the extremely sparse regime. Right? If I do Pn is equal to n to the C by n to the alpha, I'll get n to the 1 plus alpha times C. So there's a C here. And if I go to the dense regime, I'll just get n squared times p. So by modulating this p, this simple model will cover all three regimes: the extremely sparse regime, the sparse regime, and the dense regime. So I can work with this model to understand all these three regimes. Okay. So this has been done mathematically very, very well. Structural properties are understood. For example, if Pn is C by n, you can place a value on C when the graph will become connected. You can understand isolated vertices based on the value of C. You can understand many, many properties of the graph just on how Pn is behaving with regard to n. And as n goes to infinite limit. So again, this is the n go to infinite limit is what I would call as scaling limits. This has also been very well understood. So for example, a simple calculation. A degree is binomial n comma p, right? And if p is C by n, we have seen in 12th class a little later that it goes to Poisson. So in the sparse regime, in the extremely sparse regime, as n goes to infinity, you'll get a tree, but each vertex has Poisson degree distribution. Okay. So now let's see some pictures so get an idea. So here I have put n equal to 100, p equal to 1 by 1000. So I should think of p as this regime here in the following manner. Sorry. So g and p. And here you think of p as, let's say, 0.1 by n. Okay. That's the regime I'm here at. So, okay. So if you look at this graph, when Pn is equal to 0.1 by n, the graph is sparse, we know that. But here, if you look at the graph in the simulation, you have no edges. It's essentially all isolated vertices, and there's one edge here, right? That's what the simulation gives. So just keep an eye on this. So I want to keep this eye. This is one thing. So now I want to change this 0.1 to show you what happens in this graph. This one, you want to see this one. So now in the next simulation, I've changed 0.1 to 0.75. Okay. So here, my Pn has gone from 0.1 to 0.75. Right? So immediately you see, okay, the number of edges get larger, and there are some connected components as well. There's a little large one here, there's a little large one here, and so on and so forth. So the ratio is C by n, but the C is changing. From 0.1, I've gone to 0.75. Right? Then I went above 1. And this is a famous phase transition that happens. If you're in physics, you'll immediately know this, that suddenly will pop a giant component in the graph. Okay? So as P crosses C by n, so Pn is equal to C by n, and 1 is somewhere here, 1 is somewhere here. As you cross across 1, on this side, there'll be a giant component. And it's known that the giant component is of order n to the 2/3. So many vertices are there, and there'll be lots of other small ones. Of course, my simulation is not that great, so I have the small ones there. And you can also understand the structure of all these smaller components. It's kind of a beautiful theory that one can sort of play with and understand. And you can just simulate yourself and just check. Like I've done a very simple simulation, you can just check this idea. So even in the sparse regime, extremely sparse regime, as the C moves across 1, you'll see different properties of the graph. Even though the number of edges is still order n. Then of course I come to the dense regime where you just have too many graphs here. It's just like the number of edges is too many, you can't see anything much. Okay, so let's just summarize. What made heterogeneity attractable was that there's independence across edges. So each edge functioned by itself. One edge being connected or not connected did not really affect anybody else. And that's what made the theory very, very tractable. So this is a very key feature of the heterogeneity graph that sort of works in its favor, that it's this is a key feature for mathematical analysis. And lots of very, very nice work in this area. Just one word of caution, my exposition in this area is non-standard. It's precise, but it's not complete. So, and just be careful about that. So, I'm just trying to focus on what I want to do. So now, how do I introduce dependencies? So for example, let's say I want to make sure that, let's say, if I am connected to X, X is my friend, X is a friend of Y, I am most likely to be a friend of Y as well. I want that connection to be inbuilt in the graph. I don't want it to be independently connected to each other. How do I do that? So the way I do this is called inhomogeneity or some version of dependence. So a small trick. The trick is the following. So what you do is you first have n vertices. Right? So you have 1, 2, up to n. N vertices. Right? And then what I do is I go give each vertex a label. Okay? So let's say u1, u2, u1. So these are vertices. And to each vertex, I give a label. So labels can be anything. So for example, here I will choose in my case some uniform numbers in 0, 1. So uniform. So each vertex gets a label 0, 1. Okay. Then what I do is I say the following. I say a vertex I will connect with vertex j. So the way I introduce dependency is, in the simplest form is, they'll connect with probability some function h of ui uj. Okay. What is h? H is a function I take in the beginning itself from 0, 1 squared to 0. Okay. This is what's called a graphon. Handwriting is, I can't sit and write properly. So this is how I can introduce dependencies. So I go to every vertex, I connect I and j with probability h of ui uj. So if I'm at I, the ui is introduce dependencies on all my connections locally. That's what's happening in this graph. Right? So this is what I've summarized in this slide. I have a graphon H. I go to any two vertices I and j. I connect them with probability h of ui uj. So now this is not something I've pulled out of the hat. It's very, very well, very, very applicable. So let's just go back to our early example and see how applicable it is. So for example, the heterogeneity graph is included in this graph itself of G and H. Because if you just go back here, let me just pull this up. Let me just copy this so I can keep it for us for analysis. Let's keep this background. So what is heterogeneity graph? A heterogeneity graph is just a graph in which the function h is just the constant function p. If that's the case, then you know that independence automatically is there. There's no dependencies. No matter what the UI UJs are, your connection probability is going to be P. So that's already covered in this regime. This is called a stochastic block model, in which you have this, this feature. So H looks like this. That means in the interval 0, 1, and this side, H takes the value alpha. In this side, takes delta and beta. So on and so forth. Since I'm an undirected graph, I want some symmetry across the axis. That's why I have this the same value delta on the other side. So what am I doing here? So what I do is, I have my labels U1 through UN, right? This is what I have. So let me go back here. Let me copy this. So I have my labels U1 through UN. So what I will do is, if U1 is below the value gamma, then I will mark it with a square, the asterisk. If it's above the value gamma, I'll mark it with a blue, let's say. And then let's say go on, and then let's say the last one also is an asterisk. So what I do is, I end up having is, I have two communities, right? One on this side, so which is, let's say, a bunch of people with all these crosses, in this case 3. And then I have another community blue on this side, which is, let's say, all these dots. Right? So the dots are on this side of gamma, if UIs fall here, and the orange is the star if they fall here. So what this graph is telling you is that, this graphon is telling you is that people on this side are all going to be connected with probability alpha. People on this side are all connected with probability beta. So you place an edge on this side with probability beta. And between them, you place an edge with probability gamma. Or delta, sorry. So it's a two community graph. So with various H's, you can play with the structure to get whatever graphs you want to get. Okay. So now I've come to the topic of my talk in the last 15 minutes or so. So I want to introduce dynamics in networks, right? So I want to understand how networks are changing in time, and I want to work with the models that are developed in a systematic way. So I have a discrete graph G and H. Now, and I want to introduce some dynamics at G and H, which I've already said to you so far. So some dynamics I'll do, I'll get G and T. Now, as n goes to infinity, it gets larger and larger, the graph, and I want to understand if it introduces some dynamics in the graphon that I've chosen, and vice versa. If you give me a dynamics in the graphon HT, can I get a dynamics in the HT? That's what I want to do. Again, so the formal idea is the following. I have an H here on this side, from 0, 1 square to 0, 1. And from this, I have sampled some graph. Let's say I sampled a 3-vertex graph. I get something like this, and I get a triangle, something like this, let's say, and then I come down here. I get a triangle, let's say, and these are my vertices. This is the graph I get G and H. I want to play with the edges in G and H over time, and I want to let n go to infinity, and I want to see if I get an HT here, which mirrors my dynamics coming from. I put a T here, or I put a T here. I want to see if I can do that in a clever way. And this must happen in an organic way. So I have to specify discrete dynamics to get me a dynamics in the H. That's the idea. Okay. Why is this problem important? It's very, very applicable. If you want to model social network evolution, this is the only way to do it. If you want to understand how pathogens spread in the network, this is one way to understand it. For example, since we are in the pandemic, a lockdown is one in which you cut down edges. That's what a lockdown does. So if you're modeling an epidemic on a network, lots of edges disappear. So the infection will be localized and disappear locally in the graph. One can understand that very, very nicely in the graph. Twitter, your company is always looking for a vertex to place a message on, so it spreads fast in the network. Who follows whom is very important, how many degrees they have, and where to place messages. There are many agent-based models that work on this setting. So that's where application is concerned. The mathematical theory is very, very nascent in the dense graph regime. in the sparse graph regime, there's lots of developments. There's many techniques to understand them. Like I showed you in the Eder-Shreni graph, the Gn where C by n, where C is the very well understood properties in terms of C. Same way in the dense graph, in the sparse regime, you can introduce interesting dynamics. You can work locally with the graph to understand what's going on and play with the dynamics there. You can't do that in the dense graph regime somehow because there are lots of edges and you can't locally play at a vertex and assume they'll have global structures in the graph. Because you have n squared edges, if you want to see interesting dynamics in the limit, you have to alter n squared edges. You can't alter n edges and assume you'll see it in the limit. Okay. Let me show you why that's the case. So I'll begin now the mathematics part of the talk in the last 10 minutes. I hope it's not too dense. So if I want to do dynamics in a graph, first I have to understand how to compare two graphs. Right? Because if I want to say one graph is close to another, I must know how to do that first, before I understand how the graph is moving. So for that, I have to introduce a notion of distance in a graph. So you can say, you and I may have our favorite distance of two graphs. They have to look exactly alike, or they have the same labels all the time as well. You can have that level of perfection of two distances. Or you can have a macro level distances. What I will do is, I will compare only subgraph counts as my signatures for two graphs. So what I'll do is, I'll look at the number of copies of F in my graph, and I'll normalize it by the number of copies of F in the complete graph. Okay. So that's a density. So for example, let's say you take F2 to be, let's say, you take F2, which is just, let's say, if I want to look at the number of copies of F2 in my graph, what am I doing? I'm going to my graph and seeing how many edges there are. So TF2 of G is just the edge density. Right? I can also do other graph. Let's say I want to know number of triangles in my graph. So I can take F3, that will be my triangle. So TF3 of G would just be the triangle density. So these are going to be my signatures of my graph. So I'm going to look at all these density structures and see how they are moving and tell you how the graph is going to move. Okay. That's all I'm going to do, formally speaking. Even though the mathematics from here becomes incomprehensible, that's the only thing to understand. In the dynamic picture, all I'm interested in seeing is how these signatures are moving. And I'll show you a theorem in the end that these signatures will tell you how the graph is moving as well, and vice versa. So here's a simple simulation I've done, and I've marked the triangles in blue. Okay? So I've drawn my graphs, and I've taken various p's. Here p is very, very small compared to 20. I think p is very, very small compared to 20. So you have no triangles. The graph is just isolated vertices here. Here p is a little bit larger, but still small, but a little bit larger. You see some triangles in the graph. Okay. And here p is quite large, a constant, so p is a constant, so you see lots of triangles in the graph. In fact, the graph is connected, and every vertex is involved in a triangle. Here, for example, these vertices are not involved in triangles. Right? They're standalone vertices. Right? So triangle still gives you an idea how the triangles is a good object to keep in mind. They sort of once your edges is sort of not a good factor for all p's, but triangles are a good factor for all p's. So this is a well understood subject of triangle counts. You can look at how the number of triangles concentrates to its mean, which is just n cubed p cubed in the Eder-Shreni. You can understand this very, very well. There are papers on large deviations on this now. Precise lake functions of how far the number of triangles is from n cubed p cubed. You can understand this very, very precisely. Okay. So now my pitch to you is, even though without a theorem, is that the subgraph density counts are the correct ones to look at. So I will compare two graphs by comparing all the subgraph counts. So if all the subgraph counts are close by, I will deem the graphs to be close. Okay. Of course, I haven't written it like a metric, but one can phrase this as a proper metric. So this I have not done. One can phrase the G, and you can place it as a proper metric space. And this is a compact metric space if you add the graphons into it, and it's well understood. So Right, that's right. So it's a good point. I can compare two graphs with not same number vertices also. Because after let's say n is 3, if I have a square, there's no copy of square in the 3 graphs. So TFG will be 0.
But then I have a question which may be naive.
Yeah.
I mean, if you have all the vertices listed,
That's right.
I can call them I, J, whatever, right?
That's right, yeah.
And then if they are connected, I just assign 1, and they are not connected, I put 0.
That's right.
And then between the two graphs, I can have something like a Hamming distance. If
Yeah,
I take a product, and that will give me the distance between the two graphs.
That's right. So
that will be much simpler, isn't it?
that's correct. That's correct. But I'm looking at a graph with lots of edges, order n squared edges. So I don't have to be so fine about it. I have not justified the claim why I should look at subgraph counts. But the key idea is that for my theory to work, I need this space to be a compact metric space, and this metric gives me that. Okay. In your case, that may not give me that. I don't think, I'll just work a little bit to show that the structural properties in dense graph theory come from the fact that you use a subgraph metric. Okay. And for example, like I didn't say why. Why did I go pick an H? I could have done any other way of connecting a graph dependencies. I picked a Graphon H. So what you can show is that the limit points in this subgraph metric are your H. Those what make the space compact. That theory is there in the background, which I have not illustrated to you. That's why it seemed artificial I'm putting this metric on it. Like I said, the exposition is not complete. It's going through a direction I want to get to.
Thank you.
So now, okay, I will skip this slide because I'm running short of a little bit of time. What you can actually show is that there is a law of large numbers limit that if you look at the subgraph density of G and H, they will converge to this integral. This is something that is good to do, but I will, since I want to show something else in the last 5 minutes or so, the law of large numbers limit that will show that the subgraph densities will actually converge to these integrals. So I will not illustrate why this is important, but this sort of gives you a topology on dense graphs, which is what I'm after. So I have 35 or 40 minutes for my talk typically. Okay. So let me show you a simulation of this idea that I want to simulate this idea. I want to introduce a discrete dynamics and show you what happens in the limit. Okay. So let's take a simple graph. Okay. So I take my Edo-Shreni. I want my piece to diffuse in some manner, and I want to understand what the graph is doing. Right. So let's go here. So let me show you this graph. Maybe before that, let me just come back here 1 second. So what am I doing is I'm making PT move like a diffusion. I will show the diffusion in a second. It's like a Rite-Fisher diffusion. dpt is theta minus pt plus square root of that's what I'm making my pt do. And while looking at the simulation, just try and see. I have marked the triangles in the graph. You should try and see how the triangles are fluctuating. And you should also see how many components are there in the graph, just to understand what's going on. So if you look at the simulation, the P is moving around on the top. And the bottom, I'm plotting the graph I'm getting, right? So you can actually see, in some cases, this is stopped? No, it's stopped. That's interesting. Okay, my iPad is frozen. Okay, let me go back again. Okay, let's see if it comes. Okay, I need the internet. Okay, it's come. Very good. So you can now see that as the P moves around, I have marked the triangles. So if P is close to 0.5, I see lots of triangles. But as P gets smaller and smaller, I see isolated components, and I see people outside triangle regime. Right? But the key thing to observe, of course you cannot see in the simulation that goes around, is the following. That as P is diffusing, of course you cannot calculate runtime unless you're very, very smart, I guess, that even the triangle count is diffusing. We can't see it in this graph, but that's what's happening in this So this shows you that I can work with the triangle counts or the subgraph counts to understand how the P is moving and vice versa. Okay, it's a picture proof, but I've done that. So now P is very, very small. You see many, many things. So let's just do it once more and just check it ourselves, what's going on. It's an important example to understand that as P is diffusing, to keep in mind how the triangles are diffusing or not. That's a key understanding. So as P gets smaller and smaller, you'll see lots of components that are hanging around separately. There are a lot more yellow guys who are not part of the triangle structure. Only if P hangs around 0.4 or 0.5, you'll have triangles and so on and so forth. So it gets small, you can just see this. As it gets lower and lower, you'll see many, many isolated vertices and so on and so forth. So now we saw some pictures were completely isolated, right? There's no triangles at all. And then P will climb up as a diffusion and it will get more diffusion. Quite nice. So now, how does one do this, right? How does one do this? How does one start with a GNP, make a dynamics that looks like a PT dynamics? That's the hard part. You can't do something naive. You can't go and turn everybody active, everybody inactive once in a while to expect this. You'll only get a deterministic equation. You have to do something drastic. So the last 5 minutes, last 2 minutes or 3 minutes, I'll explain that idea and I'll stop. So suppose I want to develop a dynamics in which this person is diffusing in a two-community graph. So the way one does it is, you introduce what's called a Moran model, in which each type is 0 or 1. And at rate 1, each person imitates a type chosen from the population. So that's called the Moran model in population genetics. And all you do is you keep track of the number of individuals type 0. Then it's known in probability that the fraction converges to right facial diffusion. This sort of a theory is available for you. So what I do is I construct my graph in the following way. I connect two vertices I and j if they are of the same type. Okay. If they're not of the same type, I don't connect them. So all I'm doing is I'm doing a graphon in which I have a square. Here's the proportion of people on this side, let's say xn by n on this side. And everybody here I connect with probability 1. And everybody here I connect probability 1. And the between guys I do 0, no connections at all. That's all I'm doing. That's the graphon I'm doing. So and then this person is going to move because this person depends on time. Right? And if you just do a simple calculation, you look at the number of copies of f in the graph, it just looks like xn power k and n minus s to power k, because in each of these places I have a complete graph. So this is the order of the graph. And now this person will converge to the right facial diffusion by our theory in probability. So what I have shown to you is that the limiting graphon looks like this, where this person is doing a right facial diffusion. So just to summarize the slide, I've given you a Moran model on the vertex set of type 0s and 1s. I look at the fractions of zeros. I connect people with zeros and connect people with 1s. I don't bother about in-between connections. If I do this, then I will get a marker process on the graphon space that's defined by TFHS, which gives by this graphon. That's the idea. So this is how we generate lots of edges changing at the discrete level. So you can do many, many funky things, m equal to 3 as well. I'll show you one simulation and I'll stop with that. Let's see if I can get it out. Let's see if I can get it out. I may not be able to get it out. Let's see. Okay, maybe I can't get it out. You can do an m equal to 3 simulation as well and do this the same idea. Mathematically, you can proceed as m equal to infinite limit. You get what's called the Fleming-Vio model. So you'll have lots of vertices and then each of them doing something funky and giving you a reconvergence and so on and so forth. And dynamics is hard. It was hard to get this idea. We were not the first to try it. You can use what's called the Aldous-Hoover theory. But if you do that, what happens is that the theory uses too much information. You'll only get jump processes or deterministic flows. There's a nice survey by Gerhard Czerny and Anton Klomovsky that you can look at to get this idea of why it doesn't work. So we were the first ones to establish this idea of subgraph density convergence, the signatures, and the sort of problem structure of tightness and process convergence and so on and so forth. So now we're looking at, so in the example that I gave you, the types fed into the edges, but the edges never fed back into the types. So if you do the double layer connection, the problem gets much, much harder to do. That's what we're working on right now, and it's a very interesting area to think about. Okay, I think I'm at the 40-minute mark, so I think I'll stop and take questions. Thanks.
Thank you. Let's thank the speaker. So we have some time for questions. Eknath.
So, sorry, I had a naive question going back to the beginning. So why was it that you called it a large block or something? That why was it n to the 2/3? Is there some heuristic for that when that large block appears? That's right.
Sorry, is Mike? Yeah. Why does the giant component have that size?
N to the 2/3. Yeah. There's some heuristic reason for that.
Heuristic reason why that's the size. The 2/3. Why do 2/3 come in? It's missing my memory right now. There is a reason in terms of the proof how the random walk breadth first search works, but why 2/3? I have to think a little bit. I don't know.
Sure,
Maybe
sure.
Deepak might know exactly what 2/3 is.
I guess the 2/3 will be at the critical point.
That's right. At c equal to 1, but he's asking why 2/3.
Okay, that's a detailed calculation.
That's detail. I do not know why.
Only at the critical point.
That's right.
Above that, it will be proportional to n.
Yeah. At c equal to 1, 2/3 come, but why 2/3 is not like KPCS. I don't know why. It's just a calculation. So.
Yeah, I have a question regarding the fluctuations of these triangles
Yeah.
that I saw.
Yeah.
So when these are characterized, the fluctuations,
Yeah.
so if I understand that one is mid-field limit when everything is
That's
connected to
right.
everything.
Right.
So how does that change when you go to, for example, sparsely connected and
Right.
you see
Right.
triangle fluctuations?
No, so what happens in the sparse case? Sparse case, you have order n to the 1 plus alpha times p edges, right? So triangle density will be 0 essentially in the limit. So if you do a limit, you see no triangles. That's why in the sparse case, you can go locally and work with it. So your local change you can observe and play with the fluctuations locally. For example, like you can do let's say you go a simple one. Take a tree. You turn edges on and off every now and then. You will see a diffusion limit in the tree space. That's good enough because enough edges you're changing. And in the Barabasi model also, if you do a dynamics like this, you will not see anything limit. You'll see a deterministic limit. So if you want to see triangle fluctuations, you do something drastic. That's a very important point. I sort of couldn't do. For example, like this one, you have to see. For example, this is how it will look like. You have to change lots of edges like this to see fluctuations. You can't change locally. You have to change huge blocks to see. I hope that's
Yeah,
clear.
yeah, no, I understand now. Okay, thanks.
So any other question? Okay, if not, let's thank the speaker again.
Thank you very much.